Okay, we are on chapter 14. So last time we started talking about chapter 14, which obviously is acids and bases and a lot of stuff in here as we talked about last time. So we got into acids and bases. Remember that an acid is really a substance that has the ability to produce H plus ions in solution. Also remember in acid-base chemistry, H plus and H3O plus are essentially the same thing. So an acid really is, again, something that can produce free-floating H pluses in the solution, not attached to anything. Base, on the other hand, is something that can produce hydroxide ions. And same idea in solution. It's the ability of it really to produce free floating hydroxide ions in the solution. A more general definition of sort of acid and bases is the Bronsted-Lowry definition. And a Bronsted acid is a proton donor. So that will be something that will give away, obviously, a proton, while a Bronsted-Lowry base is a proton acceptor. And that is something that will accept an H plus. And remember that sort of the consequence here of our Bronsted-Lowry definition of this is, say, our acid, and this is our base. He's going to send over our H plus over here. We will make H3O plus and a little A minus action happening. It does create partners on the other side of the equation, which are related to the guys on the left-hand side. So our acid over here, its partner on the other side is the conjugate base. While I'll say the water here, which is acting as a base, its partner is the conjugate acid. So all the conjugate partners there on the right-hand side of the arrow, or your regular acid and bases there on the left-hand side of the arrow. And once again, it is only a difference of 1 H plus can be, again, the only difference there is to make these guys really partners. As we go from the acid to the conjugate base, it has 1 less H plus because it got rid of it. And as we go from the base to the conjugate acid, it has 1 more H plus because it accepted it here along the way. We talked about the relationship here of Kw, I believe, as well. And Kw is the concentration of H plus times the concentration of OH minus equals 1 times 10 to the minus 14. You could use this as really a conversion factor if you're given either the H plus concentration or OH minus concentration to calculate the other. The good news is it's really the same calculation regardless of which one you are doing. You basically take the Kw, which is that 1 times 10 to the minus 14 value, and you divide it by the other concentration. And you can compare the two concentrations there. If the H plus concentration is larger than the OH minus concentration, that means the acid part of the solution is larger than the base part. Then it will be an acidic solution. If they do equal each other, they both will have a concentration of 1 times 10 to the minus 14, and it would be neutral in that case. And obviously, if the OH minus part is larger than the H plus part, thank you, and then it will be a basic solution in this particular case. So really important, as we talked about as well, obviously, is to make sure you are using your exponent punch in when you punch these things in. Any questions on any of that stuff there? I think we talked about last time. Okay, so I think we did an example last time. So I think this is where we're at. So next we're going to talk about is actually the pH scale. And the pH scale is a measure of acidity. And the pH scale does run from 0 to 7 to 14. And less than 7 is acidic. Greater than 7 there is basic, and 7 on the nose really is neutral, and that's what we're going to kind of consider in this class to be neutral, like 7 on the nose. are super, super close to 7, like 6.999 or so. So very, very close to 7 is what we're going to consider neutral. If there's anything kind of above or below 7, we'll consider it either slightly basic or slightly acidic. 7 is sort of your center point. As you go towards 0, you become more acidic. And obviously, as you come towards 14, you become more basic. That is the formula there to calculate the pH. The pH is equal to negative log of the H plus concentration. Once again, this is another formula that you can substitute H3O plus into if you like, whichever way you want to do it. It does tell you what you need to calculate it, which is the pH. So you do need the H plus concentration to calculate the pH. Now, depending on your calculator, this formula and some of the rest that we're going to see, it will depend on how you should punch it into your calculator. If you have a display calculator, you will punch it in exactly the way this formula is written and all the other ones are written. You would hit your negative button, you would hit your log button, and then you would pipe in your number with your exponent button in most cases. If you have a non-display calculator, this equation and the other ones that we're going to see today, you pretty much need to work backwards. So you got to start with the number, then hit the log button, and then hit the negative button. If you're not sure what type of calculator you have, all you have to do is hit the log button. And if your calculator says log, you have a display calculator. Congratulations. And if you hit log and it says error, congratulations, you have a non-display calculator. So that is the way that you can determine it. So make sure that you understand how to properly punch it into your calculator, depending on the type that you have. Again, display pretty much just the way the formula is written, non-display sort of working backwards on most cases. So when we look at the pH, that is what we want to look at, which is the pH value there to determine if something is acidic, basic, or neutral. And by the way, you are when you are asked that question, there really is only one answer to that question. The solution is either acidic, basic, or neutral. It is not acidic and basic, like I've seen on many exams over the years. And I don't know if I've ever seen anybody put all three up for one solution, acidic, basic, or neutral. I don't think I have, but sometimes people will put basic and acidic for the same solution. Should only be one of those things. We'll talk about why people do that a little bit later on, but I would always look at the pH value there to help you determine it. Again, if the solution is neutral, as we talked about, the H plus concentration will equal the OH minus concentration, which means that if you have an H plus concentration of 1 times 10 to the minus 7, that again should yield you a pH of 7, which is why, again, we're going to consider neutral to be exactly 7 in this case. If we have a greater H plus concentration, we'll have a lower OH minus concentration, and we actually will get a lower pH value. So as the concentration of H plus increases, the pH actually decreases and vice versa as well. And that happens where we have a basic conditions. If the H plus is less than the OH minus, then the pH will be above 7. A reminder that in terms of the H plus concentration and the OH minus concentration, they much like sort of pH there run opposite of each other. So again, as one goes up, the other goes down in the solution. Let's talk a little bit about sig figs and pH. So the number of decimal places in a pH type of value should equal the number of significant figures in the concentration value. So the general rule is if you calculate something like pH, how far you should really take the decimal places. So we're going significant figures to decimal places here, is equal to the number of significant figures there are in an answer. So for example, if we had an H plus concentration of, say, 2.4 times 10 to the minus 3. Why don't you calculate the pH to the proper number of figures? Make sure your calculator works. Okay, so the pH here would equal negative log of 2.4 times 10 to the minus 3. Once again, you want to make sure you are using the exponent button. Otherwise, you're going to be in trouble for sure in this chapter here. And on your display there, it will say something perhaps like 2.619788758, which is clearly too many digits to give for an answer. I should take this to where? I should take it to 2.62. Yeah, so you should take it to 2.62. The number of significant figures in this number is 2 significant figures. That means that I end up with not 2 significant figures, but 2 decimal places in my pH value. So we're going significant figures to decimal places here. And by the way, we're going to talk about obviously going backwards from pH to the H plus concentration. So it works the same way going backwards. In that case, you would obviously go decimal places to significant figures. So not sig figs to sig figs in this particular situation. Any questions on that there? This obviously would be acidic, right? As we are less than 7 in this case. So. Any questions on that? All right, so there is our pH scale. And again, there's our strong base up there towards 14, a strong acid towards 0. So more acids here in the 3-ish range. We have pure water, which is 7. By the way, if you take some water that's maybe not pure water, it's been out a while, what would the pH be? Will it be 7? It probably will not. It'll probably be like in that range, right about there, and stuff like that. Especially if it's been out a while, it'll pick up some carbon dioxide in the air and make carbonic acid, increase the amount of H plus that's in the solution, and actually lower the pH and stuff like that. So sometimes your pure water is maybe not so pure and won't necessarily be a pH of 7. A lot of times it's a little bit more acidic in certain cases. Now there are some scales that are similar to pH. And one such scale is what is known as the pOH scale. And much like the name implies, you can use the OH minus concentration to calculate the pOH, which is minus the log or negative log of the OH minus concentration. The reason this is sort of useful is if you take the pH plus the pOH, it will equal 14, which gives you a little bit of a variety of ways that you could calculate some of the questions that you may be asked. We'll add our pH here that we just saw. It also means that perhaps you may not even have to use KW, which is our H plus times our OH minus. Equals 1 times 10 to the minus 14. So maybe you are given the OH minus concentration, you want the pH of the solution. You could calculate the pOH and basically just take 14 minus it, and you'll have the pH, relatively quickly without having to use KW. You could still use KW if you wanted to. You could convert it into the H plus concentration first and then go into the pH, but you don't necessarily have to in this particular case. This is a pH meter, the good old Beckman pH meter there, started a company. It measures basically the amount of free H plus ions that are floating around in this solution. And really what it does is it measures some voltages that are happening in the solution, and you give it like a pH of 4, say buffer, and go figures out the voltage for that, and do like a 7 and a 10, makes a calibration curve, and then when you put it your solution in, it goes, and that's about a pH of whatever it may be. We obviously can also use pH paper sometimes to measure the pH of a paper. So kind of like swimming pools. You ever tested like a swimming pool with a little strip there, and it'll change its colors and kind of match it up. That's sort of how pH paper works as well. You put your solution on, it changes color, try to match it to the scale of what it is. Obviously, a pH meter is much better. It gives you a little bit better of a reading when you're doing it. Now, when we talk about the pOH scale and the pH scale, They do run opposite of each other. So as we just talked about, the pH scale is 0 to 7 to 14. And once again, that is basic and that's acidic. The pOH scale also runs from 0 to 7 to 14, but less than 7 is actually basic. Above 7 is acidic, so it runs opposite. So this is very commonly the place where people, when I talked about that question a second ago of, there's only one right answer for acidic, basic, or neutral. This is very common. What people will do is they'll calculate the pH and go, cool, it's above 7, it's basic. Then they'll calculate the pOH for the same solution. It goes below 7, so it's acidic, and we'll give both answers for that. So everybody that I know of, in most cases, this is the pH scale. It's pretty much the one that they have in their head. So I would recommend always just looking at the pH value to determine acidic, basic, or neutral. Again, pOH runs opposite, and most people have the pH scale in their head. So that's probably the best rule of thumb to sort of follow. Now, in addition, if we have the pH given to us, we can directly get from that the H plus concentration. So you could calculate the H plus concentration by taking the inverse log of the negative pH. I would say probably on most people's calculators there, when you do the inverse log, it typically will put up on your screen a 10 and a caret, or how a lot of people do incorrectly scientific notation like this. So usually when you do that inverse log, that will be what it will look like on your screen. Same thing if you have the pOH, you can directly get from the pOH the OH minus concentration. Pretty much the same calculation. OH minus concentration will equal the inverse log of the negative pOH. And once again, that will probably look on your screen here, pOH. I would say on most people's calculators as well, this is going to be an upper left corner, a second button, or a shift button. And usually that is where you find the log button, where you find the 10 to the x is typically where you find that basically. So you hit those two things. Same thing if you have a display calculator, you would hit the second, then the log, and then put it in with the negative button. If you have a non-display calculator, you would have to start with the number, make it negative, and then do the second log. So you kind of, again, it has to work backwards on that equation if you have a non-display calculator. So as you can see here, we have a variety of options in terms of how you could solve some of these problems. Any way you choose should give you the same answer, regardless of sort of which path you choose. But some might be a little bit quicker than others to kind of get you there. Any questions on any of those there? Well, no time than the present to just try our calculators. So let's just do everything here. So what is the H plus for this guy? What's the OH minus concentration? We have the pH. So what is the pOH? And is it acidic, basic, or neutral? And then for the bottom one there, we have the OH minus concentration. So what is the H plus? What is the pH? What is the pOH? And is okay, so let's take a look, see how you're doing. So in this first one here, we are given the pH of 4.82. That does give us really two options right up front. Right off of that, we can get the H plus concentration. We also could get the pOH or pOH value as well. So we'll start with the pOH. So the pOH here will equal 14 minus my pH value of 4.82. And that's going to give me a pOH here of, looks like 9.18. We could also, again, get the H plus concentration here. I'm going to do the, again, inverse log of the negative pH. So once again, when you pop that into your calculator, probably should look something like this. You want to make sure you live here, 4.82. And that is going to get us something here. Minus 4.82. We will call it 1.5 times 10 to the negative 5, and it does need a molarity there. At this point, you also have two options really to get the OH minus. We could use this to get the OH minus. We could also use KW to get the OH minus. Again, whichever way that you want to kind of do it will be fine. I'll do it one more time with the kind of newish way. We'll do our OH minus here. Will equal the inverse log of the negative 9.18. And that is going to get us there. 1.8. Looks like 6.6 times 10 to the negative 10 molar in this case here. 6.6 times 10 to the negative 10. And lastly here, this is going to be acidic, basic, or neutral. This one is. We want to look at the pH, and that is less than 7, which means it is acidic in this case. Any questions on either of those calculations? Now, in terms of sort of the sig fig stuff that we also talked about, here we have 2 decimal places, which means we should really end up with 2 significant figures going backwards to our concentration. Same thing here, 2 decimal places should end up with 2 significant figures going again backwards for the pH or the POH type value. Any questions on that there? All right, looking at the bottom one here, we have the OH minus given to us. Oops, go back. There we go. So we have the OH minus, which is 2.5 times 10 to the minus 7. And again, on this one, right off the bat, you have 2 options since we're looking to solve for everything. We could get the H plus concentration using KW. We could also calculate the POH directly from that value. So that's what I'm going to do first. So the POH here going to be negative log of our OH minus concentration, 2.5 times 10 to the minus 7. And again, if we put that in correctly here, 2.5 to the minus 7, looking like a 6.60. We could then from that get the pH, which should equal 14 minus our POH of 6.60. So we'll do a little minus 14, 7.40. And at this point, again, you have 2 options as well. We could also use this to get to the H plus, or we could just go for old time's sake back to KW here. And our H plus concentration will be 1 times 10 to the minus 14 divided by our 2.5 times 10 to the minus 7. And in this case here, gonna get us, it looks like 4 times 10 to the minus 8 molar in this case here. Any questions on any of those? This is going to be slightly basic, yeah, as it's just above 7 here, Any questions on that one there? And again, you could have used our pH value as well and did the inverse log of negative 7.4, and you'll get like 3.9-ish with the rounding up to 4.0 times 10 to the minus 8. Questions on any of those? All right, let's try a few more here. I think same thing, was pretty much calculate everything. And is it acidic, basic, or neutral in this case? Here we are given the H plus concentration of 3.5 times 10 to the minus 6. So we could go right into our pH with that, minus the log there of H plus, gonna get us negative log 3.5 times 10 to the minus 6. So we're gonna hit the negative button, the log button. 3.5 exponent negative 6. Gonna give us a 5.46 here pH. We could then very easily get the pOH from that by basically just taking 14 minus the pH. And we'll do our minus 14, 8.54 pOH. Now that we have the pOH, we could also do the inverse log of it, of the negative pOH. So like a 10, a caret, negative 8.54. And they're going to get us a 2.9 times 10 to the minus 9 molar. And lastly here, we do want to make sure we look at the pH, and that is less than 7, which means it should be acidic. Yeah. Any questions on any of those calculations? Again, if you're finding yourself slightly off, but it's probably the way you're punching it in. Again, not maybe using your exponent button correctly. Questions on any of that there? So clearly, you need to be able to solve for any of those things: pH, pOH, H plus, OH minus concentrations, depending on what's given to you. Then let's talk a little bit about acids and strong electrolytes. And a reminder that a strong electrolyte is something that will 100% break apart into ions and solutions. There definitely are strong acids, which are strong electrolytes. There's also strong bases, which are strong electrolytes. So again, when we have something like hydrochloric acid, it is going to 100% break apart into H plus and Cl minus. That means pretty much in that solution, you're just going to have a bunch of H pluses and Cl minuses floating around, but really a lot of H plus into that solution really, really quickly, because none of the HCl units will stay together. They're just going to break apart. And that's different than a weak electrolyte, which basically will stay together. So unlike a strong acid or a strong base, a weak acid or a weak base, which is a weak electrolyte, will mainly stay together in solution. And you will produce a little of these ions, which means if you looked at, say, the beaker, a majority of what you would have, say, in there is acetic acid, which is what we have in this case. But you will produce a little bit of acetate in this case and some H plus. So you'll have a little bit of that floating around. So since it's able to still produce a little bit of H plus in the solution, it's still considered an acid, but you will not produce anywhere near the amount of H plus like you would with the HCl when it goes into the solution. So strong acids completely break apart. So in this case, since we do have water in the equation here, we will make a little H3O plus and Cl minus. H3O plus and NO3 minus. H3O plus and ClO4 minus and H3O plus and LHSO4 minus in this case. Yeah. Now, again, in each of these cases, we're going to get the H plus basically coming over from our acid. Water in this case is going to act as the base in this case. I think we put it up earlier, but just to remind everybody, there is sort of a list of 6 strong acids, which are really good ones to sort of remember. Hydrochloric acid, nitric acid, sulfuric acid, perchloric acid, hydrobromic acid, and hydroiodic acid. So once again, this list of 6 is kind of a good one to know because if it's not really one of the 6 here, you could probably make a pretty safe bet again that it's going to be a weak acid. So by process of elimination, those are a good kind of 6 to sort of know. And again, they are all strong acids because when any of them are in solution, you pretty much are creating a lot of free floating H plus or H3O plus in that solution. And again, that's essentially what's going to make it a strong acid. Now, weak acids, on the other hand, will mainly stay together, and we do get sort of our reversible reaction happening here with our arrows. So here we will get a little bit of H3O plus and F minus, little H3O plus here, and NO2 minus, little H3O plus, and some sulfate, and a little bit of H3O plus, and some hydroxide in this case. Now, again, most of what you're going to have in solution is everybody on the left-hand side, but they are still, as I mentioned, able to produce a little bit of those H3O plus and still considered an acid in this case. Our strong bases here have hydroxide typically in it. And I think we talked about it the other day, but just a reminder, kind of lithium, sodium, potassium, calcium, strontium, barium. Any of these guys in group 1 or 2 on the periodic table that has hydroxide in it are typically you're going to be your strong bases. And again, they also will 100% break apart. And once again, any of these guys in solution is going to produce a lot of OH minuses, which is going to make the solution definitely basic in that particular case. We also have some weak bases as well. And for example, here F minus is a weak base, which is going to actually accept some H pluses in these cases. And that's going to make a little HF and hydroxide and a little HNO2 and hydroxide. So much like our weak acids, these guys are still able to produce some hydroxide in the solution, which means they're still considered bases, but again, nowhere near the amount of hydroxide would be produced as comparison to something like sodium hydroxide, which is just going to fall apart basically and produce a lot of free OH minus in that solution. Here they gotta go find some water, do a little bit of a reaction and stuff like that. Same thing with NH3, which is a very common weak base. It again, it's got to kind of go find some water, do a little reaction happening there. Gonna make a little NH4 plus and some hydroxide in this case. Now, the relationship between sort of acids, bases, and their conjugate partners, it's a really important relationship to understand, especially as we go through this chapter. It will sort of pop up this relationship in a couple of places. So the general relationship in terms of sort of the strength of the conjugate partners compared to where they come from is this. If we have an acid or a base and they are both strong, or one of either one, strong acid or a strong base, then the conjugate base to that acid or the conjugate acid to that base will be relatively weak. So it'll be a relatively weak partner if it comes from something that is strong. The importance of that is, as we will talk about a little bit later on this chapter, they pretty much will do nothing in the solution. So they won't continue to react if you produce them. They're just going to kind of float around. They're what are sometimes considered being neutral. So if you have something that comes from a strong acid or strong base, its conjugate partner on the other side is relatively weak, not going to really continue to react, and will essentially be like a neutral sort of what's referred to as a neutral salt because of that. It's just going to kind of hang out there, not really affect the pH or anything like that. Now, if we have a acid or a base that is weak, its conjugate base and its conjugate acid in this case, obviously these guys still connected to each other, will be considered to be relatively strong. Now, when we talk about it being relatively strong, it is nowhere near as strong as a strong acid or strong base. It is strong in the sense that if they are produced in solution as a result of a weak acid or weak base being present, they will technically continue to react with water, which is also present. in a reaction we'll talk about, which is known as the hydrolysis reaction. So if you have one of those situations, those guys, either the conjugate acid or base, can continue to react with water. And the result of that is you will produce, as we will talk about, either, depending on what you're starting with, H3O plus or some OH minus. And the consequence of that is, because it continues to react with water and produce either more H3O plus or more OH minus in that solution, it can actually have an effect on the pH of the solution. It will actually change the pH and make it either more acidic or more basic, because we have this guy continuing to react with water, which is obviously in the solution to begin with. So that's a really important relationship to understand, especially when we get to salts and we talk about hydrolysis sort of equations and reactions that we're going to talk about. So anything that comes from a strong acid or strong base, pretty much going to be weak, nothing much going to happen with it. You really don't have to worry about it affecting the pH of the solution. But if you do have something that came from either a weak acid or a weak base, that thing you do have to sort of worry about in terms of the pH of the solution, because it will definitely affect the pH of the solution. As we'll talk about, sometimes they refer to the strong base relationship as anything that comes from group 1 or 2 on the periodic table, besides beryllium, because that's where our strong bases basically come from, group 1 and group 2 on the periodic table. Any questions on that there? So here's a table from your book. Again, our sort of strong acids over here, and their weaker conjugate partners on the right-hand side there. And then vice versa here, our kind of weaker acids and our stronger sort of bases going that way. So again, sort of an opposite relationship in terms of partners and, their sort of acid strength. So as we talked about here, strong acids will completely dissociate, and a weak acid will mainly stay together. As we can see here, weak acid mainly staying together, strong acid completely breaking apart. None of those guys still really floating around in the solution. All right, so once you calculate this, this is actually what is the pH of 2 times 10 to the minus 3 molar nitric acid? And what is the pH of 1.8 times 10 to the minus 2 molar barium hydroxide? That is a strong acid and a strong base. Yes, so let's calculate the pH in each of these cases. Okay, so let's take a look. So in this case, we don't have like a generic H plus or OH minus given to us. We actually do have a actual acid given to us. Again, we should be able to recognize this acid as a strong acid, which means that when it is in solution, it is going to 100% break apart into H plus and nitrate here. And remember that we are looking for the pH, which is negative log of the H plus concentration. So really, in terms of the pH, it is the H plus concentration that is the most important here. We do know the concentration here of the whole thing, which is 2 times 10 to the minus 3 molar. If you understand, hopefully, concentrations, I think we might have talked about it at the beginning. It is a 1-to-1 relationship between that and the H plus, which means essentially you take 1 times the concentration or keep it the same, which will give us a H plus concentration of 2 times 10 to the minus 3 molar, which is really all we need here for our pH. So we could go into it negative log of 2 times 10 to the minus 3, and here 2 minus 3. Looks like a 2.7 here in terms of our pH. And that is an acidic pH since this is an acid. So that's good, right? You get a basic pH here. Something probably went wrong. Question on that there. Just a reminder that if you're not sure about this whole concentration thing, let me just show you the longer calculation to remind you. We basically have 2 times 10 to the minus 3 moles per liter of nitric acid, we basically are just going to do like a mole to mole relationship. 1 mole of the whole thing there gives us 1 mole of the H plus. Moles of the whole thing cancel, gives us 2 times 10 to the minus 3 moles per liter of H plus. So kind of like stoichiometry, basically. And we end up multiplying the concentration by 1, basically, which is what we did there. Any questions on that there? Looking at the second one here, that is barium hydroxide, also going to be a strong base. So when it breaks apart in solution, we will have a barium ion and 2 hydroxide ions, as the 2 here will come out to the front of it. That's basically what that means. You have 2 hydroxides. In this case, it's actually the hydroxide that's going to allow us to get to really the POH and not the pH directly. But once we have the POH, we can then get to the pH through that sort of pathway. And in this case, we have 1.8 times 10 to the minus 2 molar. It is a 1 to 2 relationship here, which is important, which means we do actually have to multiply the hydroxide concentration by 2 to get the proper concentration, which would be 2 times 1.8 to the minus 2, 0.036 molar here. At this point, we have the OH minus concentration, so we could go into our POH, negative log of 0.036, and that's going to get us there. Looks like a 144. Now, for some weird reason, you thought that was the pH. It obviously should not make sense to you, as that is definitely not basic, which it should be. We could then get to our pH by basically taking 14 minus our POH number here. And if we do that there, that's a 1256, which is definitely basic and what we would expect in this particular case. Question on that. So sometimes they may actually just give you a formula. And if it is a strong acid or strong base, you really need the H plus concentration or the OH minus concentration so that you could go into there. I would say probably in most cases, since most of these strong acids are monoprotic, whatever the concentration of the acid is, will be the H plus concentration. Probably more so the bases, you might have to adjust a little bit like we did here. It is the same sort of calculation as above, so if you want to see the longer version of how you get to the concentration, we have 1.8 times 10 to the minus 2 moles per liter of barium hydroxide. Once again, just going to kind of do a geometry move here. 1 mole of the barium hydroxide will give us 2 moles of the OH minus. Moles are going to cancel, and that gives us our 0.036 moles per liter of hydroxide. Also why we are multiplying by 2 basically here by doing it that way. Any questions on how to get the pH of a strong acid or strong base? All right. Again, some lists there of our strong acids, strong bases. Probably a good idea to kind of know those. Again, that's just a process of elimination at that point. Everything else probably going to be more of a weak acid or base. So speaking of weak acids and weak bases, we do handle those a little bit different because they are weak acids or weak bases and really weak electrolytes. They do set up that equilibrium. And if they set up that equilibrium, there should be an equilibrium constant. And as you might also guess, there should probably be an ice table following that whole deal. So when we have a weak acid like this, we can write a K expression for it, an equilibrium constant expression, which just like everything else, are products divided by reactants. This is what is known as a Ka, adding to our ever-growing list of K values. We have Kc, Kp, Kw, now Ka. And it is the equilibrium constant for a weak acid. And as the Ka value increases, the strength of the weak acid also increases. And that's because even though it is a Ka value, it is still an equilibrium constant value. And when I have a large value of K, do I have mainly reactants or products at equilibrium? I mainly have products at equilibrium, right? And if I have a large value of Ka, that means I mainly have products. And if I mainly have products, that means I have a lot more free H plus floating around. So it will make it a stronger weak acid because of that. Once again, it is nowhere near the strength of a strong acid. So in comparison to other weak acids, the one with the larger Ka value will be the stronger weak acid, if that sort of makes sense. Um, and vice versa as well. If you have the smaller Ka value, you will have a weaker weak acid in comparison. We find Ka values for weak acids. Will we have a Ka value for a strong acid? The answer is no. Yeah. And that is because a strong acid like HCl will 100% break apart into H plus and Cl minus. And that means that it is a one-way street. All you have are products. There is nobody going back the other way. So you have really no equilibrium. So you do not have a Ka value for typically strong acids in this case. That is another way that you could recognize if you're dealing with a weak acid or a strong acid is if the problem gives you a Ka value, or you can look at the Ka table and find the acid in there, then you know it is a weak acid. Again, typically strong acids will not have it. The only maybe strong acid you might find in a Ka table is sulfuric acid, since it's a diprotic acid, and it will give you a value of usually very large, which is not very helpful. So we usually don't worry about sulfuric acid as it is still considered a strong acid, but it is found in the table because the second hydrogen that comes off is a weak acid, that HSO4 minus. So that's probably the only strong acid you might see in the table, and you probably will not have a value given to you other than, hey, it's kind of large, so which is not really great for calculations. You can't really put large in your calculator and do those type of things. So see a Ka value, super big hint, dealing with a weak acid, which means you're going to do an ice table. Yeah. And the ice table here is pretty much done like normal. We will use molarity. We will use X's. We will solve for X. And when you solve for X in these type of problems, we're usually interested in the pH, which means when you do solve for that X, that is usually the H plus concentration, which means you can directly go into the pH formula at that point. So they are solved really the same way as an equilibrium and ice table that we did in the previous chapter. The main difference is we're usually kind of interested in pH, so kind of interested in that X value, which is the H plus, and then go into the pH sort of formula. That means you could also solve it all the ways that we solved the previous ice tables: perfect square, quadratic, assumption if it's possible. So you can use all those sort of methods, obviously, that we used in the previous chapter. Here's a table from your book of some Ka values. And as we go through them here, you can look at it. All right, so why don't we try one here, see what you come up with. So what is the pH of a 0.5 molar HF solution? The Ka value will use 6.4 times 10 to the minus 4 for HF. All right, so again, I see a Ka value, I see a weak acid, I see an ice table. Go for it, see what you come up with. So a couple things when you look at this problem, we have HF, we're looking for the pH. Once again, we do see a Ka value, so that automatically should scream to you that it is a weak acid. Just secondarily scream to you that you should probably be doing an ice table as well to solve this. So we'll start with our weak acid, which is going to dissociate and break apart into H plus and F minus. You also write our Ka value here, which would be H plus and F minus divided by HF. and that's going to equal our 6.4 times 10 to the minus 4. So initially here we got 0.5. We're going to do zeros like a kind of a normal table here. We're going to have a minus x, a plus x, a plus x. That means when we reach equilibrium, 0.5 minus x, x, and x. Questions on the ice table here. Once we have it like a normal sort of equilibrium problem, we're just going to kind of throw everybody into our expression here, and that is going to give us x squared, not 2x, by the way, x squared, x times x. 0.5 minus x will equal 6.4 times 10 to the minus 4 in this case. I'm going to assume that x is equal to 0, as that is a small value of k, so we can try our assumption here and see if it works. So if I do that, that will reduce this down to x squared divided by 0.5 is equal to 6.4 times 10 to the minus 4. I'm going to multiply that to the other side, then I'm going to square root it. And if I do that there, 5.5 times 6.4 to the minus 4. That's going to give me basically x squared is equal to 0.00032. Little square root of both sides. Going to give us an x value of 0.01789 in this case. Remember that when we do make the assumption, we should check it because, again, it may not always work. To check it, we're going to divide our x value by what we were going to subtract it from and times it by 100%. And in this case, if we do that and times it by 100, it's like 3.6, which means our check is good in this case. And because our check is good, we could go to our here and we see that x is equal to our H plus concentration, which means essentially our H plus concentration here is 0.01789. And that is all we need to go into our pH minus the log of 0.01789. Oops. And do a little bit of that. And 0.01789er. Gonna yield us here, we'll go with 1.7 in terms of our pH in this particular case. That is acidic, which is good since we are dealing with a acid in this particular case. Yes. You can't do an ice table because there's no equilibrium value for it. But you could still use an ice table to help you figure out how it breaks apart if you need to. But you wouldn't do it in sort of a traditional ice table sort of calculation because there's no real K value associated with it. Yeah. Other questions? Yeah. What's that? It is. But the pH in terms of its value is, how to say this correctly, not necessarily relatable to something being strong or not strong. So it is dependent on sort of the concentration and stuff like that. So for example, you could have acetic acid, which is, a weak acid, but you could buy like, an 18 molar acetic acid, which is a very strong bottle of acetic acid. So it is very strong as well. So it's not necessarily that relationship in terms of the pH, maybe with being weak or strong. Yeah. Other questions? Yeah. You could assume x is equal to 0 anytime you have a k value that's small. So technically you could try it with anything that's less than 1 that has like a negative exponent. You should always check it because, again, it may not always work. And especially in these situations, it is really sort of, as we'll talk about, concentration dependent. So to touch upon that, if we had really the same problem here, the exact same problem, except that the concentration was a little bit different. So instead of, say, 0.5 molar, we had 0.05 molar. We would approach the problem really the same way. It would be a very similar ice table here, except obviously our initial concentration is a little bit different. We would have 0.05 molar. These would still be zeros. This would be minus x plus x plus x. 0.05 minus x, x, and x. Just like we did on the previous problem there, we will put this into our equilibrium expression here, our Ka value, and that'll give us x squared divided by 0.05 minus x. And once again, we'll use the same K value there that we had, which was 6.4 to the 4. So in this case, if we assume x is equal to 0, and again, we have obviously the same K value associated here, that will give us our x squared. 0.05 is equal to 6.4 times 10 to the minus 4. Once again, we're going to multiply and then take the square root of it. And if you do that in this particular case, 6.4 to the minus 4 times 0.05 and a little square root action of it, gonna give us 0.005657. If we divide this by, in this case, the 0.05 and times it by 100%, we end up with 11% or so, which means this is a bad assumption. So you should check it. We do use, again, that 5% rule, which means if it's 5% or less, you're good to go. In this particular example here, we would need to go back and solve it some other way, probably the quadratic formula in this particular case. The reason there is a difference, even though it looks like the same thing, and they both have 5s in the concentration, is the difference in the actual concentration of, say, the first problem versus the second problem. In the first problem, the concentration is much larger, like 10-fold times larger than what we have here. So if you think about it, when we make the assumption, the idea is if it's less than 5%, then the change is all not that all important. It's kind of negligible, the change is going to occur. So when we have a larger concentration for something like an acid, that little bit that comes off is going to be relatively small and compared to, the whole thing. So like if you had a pizza, you had a whole pizza, brand new pizza, you take one slice out, right? Still have a pretty good amount of your pizza still left, right? Not a big amount of change is sort of happening in terms of your whole pizza. Now, if you lower your concentration, any little bit that you lose is going to be significant because you're starting with a much lower concentration. If you go back to your pizza example, if you're down to only 2 slices of pizza, right, and somebody takes one, still only took one away, right? Now you just took half of what you started with, right? So a much bigger proportion based on what you started with in terms of the concentration. So concentration is really important in terms of whether or not, for example, those sort of assumptions will kind of work or not. And in this case, because the first one was much larger than the second one, it actually works. So the take-home message here is you shouldn't just autopilot and just assume that the assumption will always work. You should take that moment and make sure that you do check it because it may not always work. Any questions on that there? All right.